Hello everyone. I'm now going to show you how to compute second-order partial derivatives. So when you start with one function of two variables, you have two partial derivatives of first order, so f of x and f of y. But of course, these two functions are brand new functions of two variables also. So you can reapply this process. You can start with f of x and differentiate f of x with respect to x or with respect to y. And you can start also with f of y and differentiate that function with respect to x and then with respect to y. So this means that there's four second derivatives, or there's four second order partial derivatives. And this is what we're going to cover in this section, how to compute these second derivatives. Again, no new rules of differentiation. It's just like before, when you compute the second derivative, you just redifferentiate your answer. You just have to be careful not to make any mistake in the process. So here are the four partial derivatives of second order. So the first one, f of x. So this is the partial derivative f of x that you redifferentiate with respect to x again. So this notation really reflects on, okay, you're taking the function f of x, so del f over del x, and you're computing the derivative of that function with respect to x again. And I'm going to use in this section mostly the f sub xx for the notation of those second partial derivatives. So I'm using the sub-index notation, but you should understand when you see f of xx, it means you're taking f of x and you're computing the derivative of that function again with respect to x. Same thing for f of yy. If you look at f of yy, what you're doing with f of yy is you're taking f of y, so del f over del y, and you're computing the derivative of that function with respect to y again. So now you can also do f of xy. So f of xy is what? You start with f of x and you differentiate that function with respect to y. And the last one, f of yx. So f of yx is you start f of yx is you start with f of y, and then you differentiate that one with respect to x. So be careful with the order here. So like sometimes people tend to confuse the order. So for example, f of xy is you start with f of x and you compute it with respect to y. All right, so the best way to understand these is by looking at some examples. First example, suppose f is 2x5 y squared minus x cubed minus y4 minus 5xy plus 1. Let's compute all the second order partial derivatives. So, of course, if you're asked to compute the second order partial derivative, you have no choice to start with the first order partial derivative. So if you start with f of x, so if I label my x's in my f, I have x5, x cubed, and x. So the derivative of x5 is 5x4, so you're getting 10x4 y squared. Then the derivative of x cubed is 3x squared, so you're getting minus 3x squared. y4, babayla, is 0. Minus 5xy, because the derivative of x is 1, you're getting minus 5y, and plus 1, babayla, is going to be a 0. So that's my partial derivative with respect to x. Now, if you're doing this with respect to y, let's label the y terms. I have a y squared, a y4, and a y. So here we go. So if you differentiate y squared, you're going to get 2y. So you're getting 4x5y, x cubed, babayla, and then minus 4y4 is minus y4, sorry, is going to become minus 4y cubed. And then for minus 5xy, because y goes to 1, you're getting minus 5 of x. And then the plus 1, babayla, is going to get 0. So I have my partial derivative with respect to y. Now let's compute the other ones. So let's compute f xx. So f of xx, the first thing you have to realize here is that I'm starting with f of x, and I'm going to compute the derivative again with respect to voyons la misère avec mon marqueur, and then I'm going to compute again the derivative with respect to with respect to x. So I just label my terms. I have x4 and x squared. So when I differentiate, I get 10 times 4x cubed y squared minus 3 times 2x and minus 0, which simplifies to 40x cubed y squared minus 6x. Again, here, nothing too difficult. Just be careful. Remember, when you differentiate with respect to one variable, the other one is just a coefficient or a constant that you keep or you send to 0. So what is fyy? So here again, make sure you see that inside, I'm starting with f of y, and I'm going to compute the derivative of that function again with respect to y. So let's label the y terms. I have 1 here and 1 here. The derivative of y is 1, so we get 4x5 times 1. The derivative of y cubed is 3xy squared, so you get minus 4 times 3y squared, and the minus 5x, it's gone. So this simplifies to 4x5 minus 12y squared. And now for the other two, and something special will happen here. So what is f of xy? So again, here, very, very crucial. You're starting with f of x, and you're going to compute the derivative of that function again, but now with respect to y. So you need to label the y terms, and you compute the derivative of those two terms. The derivative of y squared is 2y, so you're going to get 20x4y. The minus 3x squared, with respect to y, and minus 5y is going to go to minus 5. And now, something very interesting is going to happen here. If you compute f of yx, so you're starting now with f of y, very, very crucial, and you're going to compute the derivative of that function with respect to x now. So let's label the x terms. So the derivative of x5 is 5x4, so you're going to get 20x4y minus 4x cubed, goes to 0, and minus 5x is minus 5 times 1, which is minus 5. And when you look at f of xy and you look at f of yx, you can see that these two things are actually equal. And this is not a coincidence, and this is actually going to be stated as a proposition. So if you start with a function of two variable f, and if the second order derivatives are all continuous function, which simply means in our case, it's going to happen all the time. You don't need to worry about restriction in this class. Then the second order partial derivative f of xy is always going to be equal to the second partial derivative f of yx. And this is very cool because this gives you options now when you're computing a second partial derivatives. Either you go the lazy route where if you are asked to compute all four, you compute f of xy, and then you just say, well, it's equal to f of yx, and then you're just saving time and you're avoiding one computation. Or if you're clever and you're more careful and you're more concerned about, like getting the right, sorry, I got emotional there, to get the right answer. Well, if you compute f of y and f of xy and f of yx, and they both coincide, then the chances are that the full computations behind f of x, f of y, and the rest is actually correct. So it's a good verification tool to compute them separately and hope that they are equal at the end. So it's always like a joyful moment when these two coincide. It's like, yay, you guys are the same. So anyways, got too excited there. So let's do another example. All right, next example, classic question. Find all the second order partial derivatives of f equal to xe to the power of y minus ln of x squared plus y. So this question starts with the first order partial derivatives, of course. So here, let's compute first f of x. So for f of x, well, the derivative of x here, so I'm just labeling my terms. So I have an x here and an x squared. So the derivative of x is just 1 times ey. Ey is just a coefficient here. And now minus, now what do I have? I have ln of something. So actually here, I'm going to summon the chain rule. If you have the ln of something, and because inside that ln, there's a variable, there's a term that depends on the variable x, I'm going to use my chain rule. So I'm going to get 1 over, so 1 over x squared plus y times the inside derivative. Of course, at some point you're comfortable. So what is the inside derivative of x squared plus y? It's simply 2x plus 0. So that's my partial derivative. I can simplify it if I want to. So I have the 1 will just be gone, minus 2x over x squared plus y. Actually, here I will also write this as ey minus 2x times x squared plus y to the power minus 1. Because here I can kind of foresee that I'm going to compute the derivative of this function with respect to y again, and I want to avoid, the quotient rule, and with respect to y here, there's only one y at the denominator. So here, you don't have to do this, but this helps, like if you have like more than one way to write the same answer. So that's for f of x. Now we're going to do the exact same thing for f of y. So let's label all the y variables. So I have one at the power and one inside my logarithmic term. So the derivative of ey with respect to y is ey again. So you're going to get x ey again. And then I'm going to use my chain rule again. So 1 over x squared plus y times the inside derivative with respect to y. Derivative of x squared is 0. Derivative of y is just 1. So there's nothing to multiply with afterwards. But again, here I'm going to simplify this. Not simplify this, but rewrite this also this way because I want to avoid quotient rule as much as possible. So I'm bringing that term up. So this is just an or. You don't have to worry too much about this, but this is going to simplify some of the computations in a moment. So now those are my two first order partial derivatives, f of x and f of y. Now let's compute f of xx. So you're starting with f of x, so I'm going to label all the x's in my first order partial derivative. I have 2 here at the numerator of the second term and the denominator, so I have no choice here to use the quotient rule. So if I start, my ey will just go to 0 because it's an expression that only depends on y. So bye-bye, you're gone. And then I have minus. I'm using my quotient rule. So here at some point, you're comfortable in your own skin. So I just have to compute the derivative of the function above, which is 2, times the function below, 2x plus y, minus the function above, which is 2x, times the derivative of the function below with respect to x here. So you're just going to get 2x. So you're getting 2x. And then all of this is divided by x squared plus y, all that squared. And because we're just asking you to compute the partial derivatives, I'm not going to simplify it. I'm way too lazy. So that's my f of xx. So now let's just focus on that one and compute f of xy. So starting with the exact same function, but now looking at the y. So I have only one of them at the denominator. So I'm actually going to use that one here in the second format so that I can just use my chain rule on the second term. So here the derivative of ey is ey again. So now for the second term, it looks complicated, but I only have one y within that power minus 1 here. So I just have to use my chain rule. So I'm going to use my chain rule. So I'm going to really illustrate that by drawing this box here. So I'm using my chain rule. So the minus 1 falls up front. It will become a plus 2x y squared plus y to the power of minus 1, which is minus 2, times the inside derivative, but here the inside derivative is 1, so I don't need to write times minus 1. So here's my f of x, y. Now let's move on to the other two partial derivatives that we compute from f of y. Here we go. So I'm going to first compute f of yy. So I'm going to compute the derivative of that function with respect to y again. So I'm going to use the second format here. So if I label my y's, so I have one y here. Whoop. Sorry, you won't see this. Okay, so you have one y here and one y here. So I'm going to use a chain rule for the second term again. So for chain rule, I like to draw boxes. That's my way of remembering that I have a chain rule. So the derivative of ey is ey again. So the x is just a coefficient. So you get x ey minus, not minus, so the minus 1 will fall up front, will become a plus 1, and then you're going to get x squared plus y. The new power is the former power minus 1, so minus 1, you're going to get minus 2, times the inside derivative, but the inside derivative here of x squared plus y with respect to y is just 1, so I'm not going to write anything, so this is going to be my final answer for f of yy. And now the moment of truth. Again, if you're a lazy piece of okay, you could just write that f of yx is equal to what we just freshly computed here, but I'm going to recompute it and make sure that these two things coincide. So if I look at my function f of y and I label all my x's, so here I have one x in front of the ey and one x squared inside that power. Now let's compute that partial derivative. So let's differentiate with respect to x. So the derivative of x is just 1 times ey. Ey is just a coefficient. And now I'm using my chain rule. So the minus 1 again falls on top of that minus up front, becoming a plus. I get x squared plus y protected. The new power is again minus 2. But now you need to multiply by the inner derivative of x squared plus 1 with respect to x. So you're going to get 2x plus 0. And of course, if you simplify this a bit, you're getting ey plus, if I put the 2x first, you get 2x, x squared plus y to the power minus 2. And what a coincidence. Okay, these two things are actually equal. So if I look at that function and that function, these two are the same. And honestly, when you are computing this in a test or something, it's good to compute them again so that when they match, chances are that you've done your job correctly. So anyways, those are all the second order partial derivative of that function. A very nice, typical, classic question for an exam. All right, that's it for that example. I have another example for you to compute all the second order partial derivatives of 3x y squared plus 2xy plus x squared. But that example is actually easier, so you can just look at it, compute it on your own. I think it's a good exercise to do anyways. So for partial derivatives of second order, remember there's 4 of them, because if you start with f of x and f of y, you can compute partial derivatives of those two functions with respect to x and y again. So giving you 4 second order partial derivatives. But remember that for all the examples that we're going to study in this class, the second order partial derivative f of xy is going to always coincide with the partial derivative of f of yx. But for that beautiful section on second order partial derivatives, that's it. That's all. Bye-bye.